right, this is section 4.4, and we want to get some intuition on this analysis of variance, and kind of where that comes from. So again, we'll just have we'll have three columns in this case, A, B, and C, and we have some data here. So I'm going to actually go with A1, A2, A3. Maybe even B. I've got B1, B2, B3, B4. And in C, I've got C1, C2, C3, C4, and C5. Okay, just to point out that the lengths don't have to be the same in each column. So what we're doing now, each of these I could make a little box plot for, and so forth. And again, as we look at the box plots, we want to kind of see, do they look about the same or not? Well, let's look at what the calculations are saying about those pictures. Okay, so this idea of analysis of variance, I mean, if we're talking about a null hypothesis that's about the means, why do we call it an analysis of variance? Well, the idea is that what we want to check is the difference in variance within a given column, and then we want to look at that difference in variance across the columns. And so what we can do is we can take all these data and we can come up with our sample mean, and that's all those data. Now I could come up with, each column, I can get a bar, a B bar, and a C bar, right? I could get averages of each of those. And what we want to check is, if we think of this variance, how does the mean of column A compare with the overall average? Now, we'll square it. That's the variance part. We will have to, I'm not going to write it down exactly what it is here, but we'll need a multiplier, C sub A, because if there are different amounts of data, we don't want a big column to sort of overestimate things compared to a small column. Okay, so we'll need a multiplier there, and that's in our formulas for making templates and so forth. And then, so we'll look at that, and a C sub, oh, C is not a good one. I'll call it R, I guess. Oh, R is not a good one either. Gosh, all these letters are used. Let's go. What letter do I want to use? How about K for now? Okay, some KA and then some KB times. So this is actually a weighted average of these variances, plus KC, C bar minus X bar squared. So that's a variance. And that is a variance between columns. Okay, we're looking at how much does the average here differ from the overall average, how much does the average here differ from the overall average, and how much does the average there differ from the overall average. Then we also want to take a look at within the columns. And so we'll look at, A1 minus A bar squared plus A2 minus A bar squared, and so forth. We'll do the B's, B1 minus B bar squared, and we'll get to the C's, C1 minus C bar squared. Okay, what this is doing is, so this is between what usually called between treatments or between columns, right? This is the variance between columns. So there's a variance. And then this is the variance within columns. And actually, what you should see is that if you take this ratio of these two, so if I call this, and now I can't think of what your book actually calls it. I gotta look here real quick to see, because your textbook calls it actually something different than what you usually see. Groups, yeah. So they do. They call this the sum of squares groups, and then they call this the sum of squares error. So I agree with the sum of squares error, but typically you call this one sum of squares treatments because it's between treatments, but you could also say between groups. Now, what's the case? The case is that if you look at the ratio of, now it's a weighted ratio, but for now, if we look at this ratio, again, this isn't exactly the ratio we look at, but generally speaking, this should be, should be small if A bar equals B bar equals C bar. And we just have some, of course, random sampling, so they aren't going to be exactly equal. But if we're sampling from the same sort of populations where these means are all the same, then this ratio over here should be small if they're equal. And it should be big otherwise. Okay, big otherwise. Now, to kind of look at that, right, let's look at three box plots, and I'll just kind of make them this way, that are essentially the same. Okay, so here are three box plots of our three columns, A, B, and C. They are essentially the same. Then the sum of squared groups, right, we would take this, we would probably get an overall average, somewhere right in here. This would be X bar, this height, somewhere in there. Then if I took the average of each one of these, the averages here might be in there. But notice they don't differ a whole lot from X bar, right? They're about the same height. If all these box plots look the same, those are going to be about the same height. And so that difference, when I look at that difference, it should be a pretty small number. And then this stuff, the sum of squared errors, I am looking at the differences here between, the X bar that we have here and, values up here, values down there, and so forth. Well, actually, as I look at this, I would expect, now again, it's a weighted average kind of thing, so it's not exactly the way it works, but I would expect, X bar here to be smaller than, the differences in, A bar minus X bar and so forth. I would expect those differences to be smaller than the differences between various values in A and its mean. Okay, that's what's going on. So this whole analysis of variance table and all that, it is just a nice formulaic way to get to a ratio that we want to check. And that ratio, okay, that ratio, it comes, that ratio comes from ratios of normal distribution. So we're still talking about this normal distribution thing. So it underlies all this stuff. But the new distribution the new distribution is an F distribution. Okay, that's what it's called. We had a T distribution. Now here we have an F distribution. We had a chi-squared distribution. Chi is just another letter. So, you know, all these things seem to just have letters for their distribution. That's not true for all probability distributions that we use, but these do. A lot of letter-based things here. And so we use this F distribution to look things up. We don't have a table in the book. We are dependent on things like Excel to get our answer for that. Okay? But that's all that's going on in this analysis of variance. Okay, is that we are just trying to look at how much the means vary across the groups compared to the overall mean, and how much the means within the groups vary. And then we're trying to look at a ratio that has to do with those two numbers. Okay? And that ratio is what we then look up in an F distribution. So that's the intuition of the analysis of variance test. Okay? Is, again, it really comes down to, let's do those again. You know, am I looking at data that look something like this? Or am I looking at data that look, you know, more like this? So, you know, as I look at these data, I would say, yep, all those columns appear to be the same. If I look at data like this, I would say, no, those columns do not appear to be the same. And, well, the question is, you know, we need a probability based on calculations that everyone would get that same probability, right? So we don't want it to just look at, you know, me look at this one and say, oh yeah, those are definitely the same. And then I look at this one and I say, you know, I think those are the same too. Whereas you might look at them and say, no, those, the second ones are different. You might even look at the first ones and say they're different, right? You know, so we want everybody to get the same answer. And so one technique for doing that is this analysis of variance. And, you know, here we've got independence. And here we have dependence, or at least maybe. Again, we'd have to actually run the test with the real numbers, but intuitively, this looks like there's a dependency between the categories and the numerical outputs I get. This looks like the categories and the numerical outputs are independent of each other. Okay, so that is what the ANOVA is trying to tell us. And so we'll stop this one there.